we were talking about stochastic gradient descent. So let me summarize. We have a score function, which is the model itself. With some parameters, it gives us a score. We have a loss function, with which we can evaluate the success of the score function. So we can optimize the loss function to find the correct parameters for the score function. A strategy would be the gradient descent. Okay, I can apply it to any function, but how to apply it to neural networks? Neural networks are not functions. If represented as graphical models, if represented as graphical functions, I should admit somebody. Sorry about that. Okay, now you're in. Okay, what I was saying is, okay, I can use my loss function and my gradient descent strategy to optimize parameters for my score function, but are neural network score kind of functions? Well, yes, we learned what artificial neurons are, how we can construct networks out of it, and actually those networks are computational graphs. So how to calculate the partial derivative of the loss with respect to parameters, because it's a computational graph, there are parameters all around the network. Well, actually, we use a method which is called backpropagation. And to backpropagate a partial derivative, what you need to do is, either using an input, you forward pass the computational graph, and you backward pass each partial derivative. At this point, you need a proper implementation of stochastic gradient descent using backpropagation to this layered network that you're looking for, right? This will be done in the very first lab of this course. Your TA will show you a PyTorch loop in which you do a forward run, and in the backward run, you calculate the losses. Okay, he will show you a code example of how it is done. When you see that code example, you will realize how those weights are being trained. But very briefly, I want to just summarize it before I give an end. So what you do is, you have an input value, and you have some starting weights, okay? So let me get to that deep learning graph I had. It would be better to show it on deep learning. Yes, this here. I have some inputs. I have a sample. I represent that sample in an n-dimensional space. If it is an apple, it was two-dimensional, right? Shape and color measure. I could use different. Maybe it's an image and I'm taking the image pixels, I don't know. And these are some layers, the hidden layer and the output layer. So the purple ones and the green ones are some neurons. Each one has some parameters. Each connection is a parameter, okay? So I randomly designate parameters, randomly. How you define and initialize those weights are an important business, which we are going to talk about in the future. I randomly designate some parameters. So if you, in a large network like this, if you randomly designate some parameters, actually you don't expect to mod the model to provide you the score function that you desire, right? Because that's random. It will give you the output of that operations using those random values. However, that's a starting point. It is very similar to the blind guy's first location. So if the blind guy is somewhere in a very strange place, he will find it's difficult to find his way. So if it is lucky, he's starting in a good place in the field, depending on the shape of the field and geometry of the field, he will easily find his position. That's why starting condition in an optimization problem is very important, which is initializing the weights. That's why initializing the weights is an open field of research and still going, and there are studies on it. We'll talk about how to initialize the weights. Let's say randomly initialized between -1 and +1, the weights are in a Gaussian distribution, randomly. What you do is, to apply backpropagation, you forward pass the network. When you forward pass the network, let me get my pen. So you had for a single sample, you have some values. So x1, x2, x3. These are some values. And these are some weights which are randomly designated. Okay? And the biases. You have some values here, right? Calculated from these weights and x's. I'm going to call these outputs of these networks actuations from now on. Okay? Actuations is the set of outputs for a given layer of neurons. I hope there's no question about what actuation is. I made a definition. So this is a layered architecture, one layer of neurons connected to the other layer of neurons. I calculate some actuations. These actuations were the green values calculated in the forward run of that simple computation graph. Like forward run values. The green values are activations. Okay. Then I calculate the activations for the here as well, because I have everything, the weights, using the random weights. Then here as well, I have all the green values. I wish I used the green, but I forgot to pen. And I have some values. Okay. Now, I have some scores here, score 1, score 2, and I calculate a loss. Okay. I want to update the weights of this layer. These are the weights of this layer. Right? These are weights here. Okay. So let's say this is the input layer. This is layer 1. This is layer 2. This is layer 3. This is layer 4. And this is layer 5. So the weights, the connections of layer 5 are the parameters of layer 5. I want to update layer 5, the parameters of layer 5 using gradient descent. Remember how the parameters were? Let's say the parameters of layer 5 is a big vector, which I called W5. How I do it was minus the step size times the gradient, which is partial derivative of the loss with respect to partial derivative of omega 5. Only omega 5, because I'm updating omega actually W5. Okay, it looks like omega. Okay, so what I have here is loss. At this point, in backpropagation, we start with a value of 1, which is presumably loss, partial derivative of the loss with respect to itself. Okay, so I have this as a function. This is layer 5. Layer 5 is a function. Let me write layer 5 is a function. So these are the actuations here. The actuations here. So this is, let's call these actuations as actuations 4. Okay, A4. So layer 5 is a function with an input of actuation 4, which is the output here, Okay? So this is the output here. I'm trying to make the definition simpler. The first thing I should calculate is the partial derivative of the loss with respect to partial derivative of the outputs. I know this. I need this. The first step of backpropagation. So let me get another pen. So partial derivative of the loss with respect to partial derivative loss, which is 1, is equal to partial derivative loss with respect to O, output. No, I don't need that. Sorry. Output. Yes. Partial derivative let me think about it. No, I don't need that. My starting point here is, so I have a loss function here. Sorry, I'm tired as well. So this is the output here. Partial derivative of the loss with respect to the output, okay? The output is the input to the loss, okay? So if I know this function, I can get the derivative of this function, right? For example, if this is a ground truth minus output, this function is, the partial derivative will be -1, right? Whatever function it is, I don't know. I can easily calculate the partial derivative. But I need to find the partial derivative of the loss with respect to parameters of 5. Okay, this is layer 5, layer 1, layer 2, layer 3, layer 4, layer 5, the output layer. Okay, so these are the parameters here. So weight 5. Because I'm going to be using it in the gradient descent. So this is actually partial derivative of the loss with respect to partial derivative of the output times partial derivative of the output with respect to partial derivative of omega 5. I'm writing too bad, sorry about that. So I know this, I've calculated here. I need this, I want to find this. This layer is actually the layer of, so layer 5 is a function of activations for given the output. So if I know the values of this layer, I can calculate this. So what I need to find is the derivative of this layer. So that's how I found this guy. If I find this guy, I'm not showing you how I did it. I calculated derivatives of the loss function, I calculated derivative of the layer. When I find this, I can apply the gradient descent like this. Omega 5 new, just like I wrote omega 5 old minus times loss with respect to omega 5. This is called gradient descent. So what I do is I backpropagate the loss, partial derivative of the loss with respect to these weights. I update these weights. Then I backpropagate the partial derivative of this loss with respect to these weights. I update those weights. Backpropagate, update. Backpropagate, update. Backward, update. Until the backward pass is finished. We have done this for a single guy. You do it for every guy in the training set, forward plus backward. And that's how you optimize your parameters. That's how you apply gradient descent to a computational graph like neural networks. I know it's so theoretical right now, but in the lab session that you're going to cover with your TA, you are going to be going over this example in code. And you're going to see the forward pass in a loop and the backward pass, the derivatives being calculated. PyTorch has automatic functions to calculate those derivatives and weights updated. And when you do this iteratively, your network will be trained. So that's the idea, guys. All we have accumulated up to now, score function, loss function, backpropagation, derivation, and gradient descent, weight update, was to get to this point, to get you guys ready for a training example. Okay, any theoretical questions? Because practical questions will be answered during the lab session. Any theoretical questions? Please. Well, your friend in the classroom is asking, was there an activation function in the output layer? Well, actually, yes, but the answer could have been no as well. With an activation function or without an activation function, this is a computational graph. Applying backward propagation of errors will not change if it is a kind of a computational graph or another kind of a computational graph. I mean, should we apply an activation function to output, if you're asking? Depends on the problem. But we are not interested in that right now. What we are trying to do is, a neural network is a computational graph, a layered architecture. We can apply backpropagation to implement gradient descent to this computational graph, one layer at a time, updating the weights of one layer at a time. If it's okay for you, then it's okay. Okay? Any other questions? Good. So let me get to my slide. So this will be the loss function, we said. And optimization, actually, the loss function is not simply a loss function. There is a term called regularization, which kind of regularizes the optimization procedure. How? Regularization is the process of adding information to the optimization, to the solver, so that the optimization will work fine. There is a so-called term in optimization, which is called ill-posed, which means the loss function you create actually creates the slope of the geometry of the guy, blind guy walking. It creates that geometry. And when the loss function is, depending on the loss function and depending on the problem, that surface could be very complex, like very, the old guy, there are so many bumps and just holes, he cannot walk properly. This phenomenon is called in optimization ill-posed problems. To make that geometry, so-called geometry analogy smoother, we add regularization terms to optimization, the loss function. When a regularization, so the aim of the regularization term in a loss function is to make that search space kind of smoother when it comes to finding the gradients, the partial derivative of the loss with respect to the weights. Because if it is noisy, those gradients will go crazy, and whatever your step size is, you will have difficulty to find. Imagine the blind guy, there are holes and pots and just taps all around. He won't be able to walk. He won't be able to find its way. The regularization function helps us to shape that geometry. I'm making very broad definitions because that's all I can do at this stage, guys, but just bear with me, okay? So this is the loss, and the regularization prevent the model from doing too well or too bad during training data. What I mean by too well, let's get back to the blind man example. There are holes and just little hills everywhere. So the guy cannot walk. He would take very small steps. He would get into a hole and think that this hole must be the only place that I can go. This is doing too well or too bad, guys. This is overfitting to that hole. So regularization is kind of the tool that we use in order not to overfit. Okay? That's what regularization is, a common term in optimization. That's what it does. There are different kinds of regularization methods. For example, one method is summing up the weights. So if I add this term to the loss function, what kind of an effect will it make? Think about it. Remember, we don't want the loss function to grow. It is like the distance of the score to the ground truth. So if I add this here, what would the effect be? Any ideas from Zoom or Classroom? If I add this weight square, sum of weight squares, what would the effect be? While, please? If the weights are larger, right? So because I'm iteratively updating the weights. If the weights go larger, the loss function will increase. Then wouldn't it make, in that iterative process, effect like pushing the weights smaller and smaller? So this regularization function is a way to control a possible explosion of weights. So you add this to make weights smaller during your optimization, kind of. You don't want the weights to explode. Or this guy, again the same. So you're trying to suppress the weight values because the weights may go crazy. And the weights, when they go crazy, it is like the old guy having very large pots and just going, it's losing its smoothness. So the weights are small, then the surface will be smoother mathematically. That's the implication. Okay?
Hocam bir şey sorabilir miyim ya? Overfitting'i mi engellemek amacımız?
Exactly.
Yani
Your friend is asking if is our aim to prevent from overfitting? Yes. So you might, it's a big jump. I know. We put the sum of weights squares, and it is preventing us from overfitting. How did we get there? I understand that, guys. I understand that feeling, and I know that you had this feeling in this week a lot. But we are making, introduction to this optimization concept. That's the way it is. So you might ask, I'm in my project, what kind of a regularization function I should be using? Well, that kind of a question will be a question within the scope of an optimization course. What you're going to do is, you are going to be retraining some type of architectures which are trained before in maybe a different type of data, and you will get what kind of loss functions and regularization methods they have used and try them and see the effects. That would be the purpose of this course, because this is an introductory level deep learning course. Okay? Any questions? And that's what I exactly say. Please, Melek. Yes, yes, yes. Well, actually, we were talking about exploding. Your friend is asking about vanishing sites. We talked about exploding site. We talked about weights exploding. And you're asking a question about gradients vanishing. Actually, they are different problems. Gradients while backpropagating vanish, not the weights. So gradient vanishing is an important problem which we are going to discuss in the following weeks. We are going to learn residual networks in the very late lectures of this course. So I put vanishing gradients aside. I'm going to answer your question first by correcting it. What about vanishing weights? If we don't make them explode, what if the weights vanish? Well, I'm going to rephrase this corrected question to, would the weights reach to zero where the model will get dead because it's a multiplication model where weights are multiplied with inputs? Well, the procedure, gradient descent procedure, will prevent that from happening, because when the weights get smaller, the loss will increase, then it will try to make them larger. So a good idea would be saying, we shouldn't initialize the weights to zero first, maybe, because it would just make the optimization procedure difficult. Yes, zero initialization for weights is not a good idea. So sorry, Melek, you asked the question, I've corrected it and went a long way to different questions, but that's the general idea that we can extract from out of it. Answer to your question? Okay. Vanishing gradients is another business which we are going to be talking about, because gradients vanish when there's a deep network. Any questions? Okay, just like I said, how will you know? Well, yes, in this level, you are going to just check the paper and do their study exactly as they do it, and maybe change a parameter, get the results and check. You are going to, deductively understand what's going on first, but we'll have an idea of what's going on inside. These are very large networks, guys. It's impossible for you to comprehend what's exactly going on. We are going to we have induced methods to understand. We'll make analysis to understand it. Okay? Okay.
Hocam bir şey sorabilir miyim? Bu solver dediğiniz şeyler aslında momentumlar, değil mi? Yani başka bir şey solver olabilir mi?
Well, actually, gradient descent is a solver. Gradient descent with momentum is also a solver. Your friend is asking, are these solvers related to this momentum concept? Did I get the question correct? Right?
Evet.
Yes, gradient descent is a solver. Gradient descent with momentum is a solver. Stochastic gradient descent with momentum is a solver. Adaptive gradient descent methods, those ADAM or similar to ADAM, RMS probe, you can see in the slide, they are solvers. So your strategy to find your weights, the strategy of the blind guy is a solver. Answer to your question?
Teşekkürler.
Okay. Which solver regularization? What kind of initialization? Well, you will first get it from the already, that at this level, we're going to do it this way, okay? In time, when you have a master's or PhD thesis on these concepts, or you're studying meta-learning in your PhD, you will study different optimization techniques, you're going to study the mathematics of it more, and you're going to get there, okay? That's how we're going to do it right now. Okay, so I think that's enough for today. I was planning to do a live coding for previously when I was preparing the slides in summer, but we have a lab, and in the first lab, we are going to be going over the training procedure. Let's do that lab next week or the other week. Probably we are going to, the other week most probably. We have to, I've spoken to Ozan and it's going to be other week. And you'll have a homework about it. When you see it happen in code, you will understand it better. So what to do until next week, I recommend you listen to this lecture once again if you are new to optimization. I recommend Stanford's YouTube class because they provide more information about different type of solvers. What is momentum? What is adaptive learning of learning rate? You don't necessarily need it at the start, but you can delve deep into it in that week of Stanford's course. And continue thinking about a project idea. And starting with next week, we are going to get into real, actual deep learning architectures. Okay, and this is the additional reading. Now, any questions about the course, about the week, then we're going to talk about projects. Any questions
Hocam,
about the lecture, please?
Ben bir şey sormak istiyorum ama biraz özel de hani arkadaşlar gittikten sonra sorsam. Evet,
okay.
proje ama...
Ece, let's leave the project discussions a couple of minutes further because maybe there are people who are going to ask questions about the slides or the lecture first. I'm going to stop recording, then we're going to discuss the projects long, okay? Okay, any questions about the lecture slides? I think Zoom people.
Sorabilir miyim?
Please.
Zamanı falan henüz belirlenmedi sanırım. Değil mi? Yoksa ben mi kaçırdım?
It's about labs, right?
Evet.
Yes, we are going to announce.
Tamam,
Most probably the other week, not the next week, the other week.
Tamam, teşekkür ederim.
Please follow OT class announcements. Your TA is also authorized to use it, so we are going to be announcing it in OT class, and you'll have emails. Okay. Lectures, I guess not.